Friends, in the last session we looked at the design of a reactor for reversible exothermic reaction, and towards the end we said that there are different ways of operating reactors for such reactions, and one of them is making use of the energy that is generated because of the exothermic nature of the reaction to preheat the reactant. So, our idea was the following, that we saw in the reactor we need temperatures at a higher levels at the beginning and then progressively reduce the temperature towards the exit of the reactor. So, on one hand we have a requirement for preheating the reactant to a high temperature, but on the other hand as the reaction proceeds there is lot of energy that is generated because the reaction is progressing. So, we can then combine these two processes, namely in order to preheat the reactant so that they enter the reactor at a high temperature, we can make use of the energy that is released during the reaction itself instead of using an external source of energy. So, these kind of reactors are referred to as autothermal reactors, and they lead to some special design features which we will see in today's session. But before we do that, let us look at how the reactor for this kind of reaction actually is operated. So, what you see here is two kinds of reactors. This one we discussed last time, that is what is being done here is the reactants are entering at this point and they are passing through the catalyst bed in this particular direction, but instead of putting all the reactants at the inlet, what we conventionally understand as inlet, let us say axial position z equal to 0, instead of doing that you have several tubes in which cold reactants are added in the middle of the reactor. So, what happens is, suppose we pass certain initial reactant over here, the reaction takes place, there is no heat removal, so temperature rises. So, then you premix with a fresh feed, so that temperature goes down and then thereby achieve the lowering of the temperature. Now, this second operation over here is the autothermal operation that we are going to look at in detail today. So, what is being done in this reactor is that this is our catalyst bed. Okay. This is our catalyst bed, but it is packed in the tubes, and surrounding this tube is a shell through which the reactant actually enters. It goes down and then there is a heat exchanger and then goes through the catalyst bed, or in other words what we are doing essentially is that if this is my catalyst bed, then before the reactants get into the reactor I pass it through the shell and then pass the reactant so that the reaction takes place. So, what happens here in this portion the reaction takes place, energy is generated, that is transferred to the reactant which is flowing in the shell, so that the reactant gets preheated before it enters the reactant. So, this is the operation which we are going to see in today's session. So, let us try to look at how this reactor behaves, and we will take help of simple mass and energy balances to understand how this reaction is taking place. So, to simplify the matter, let me just show one bed of catalyst and surrounding shell in which my reactants are going to enter. So, what I am going to do is I have my reactants at temperature T1F and concentration C1F, which are going to flow through this empty shell before it enters the reactor. So, let us say that keeping in mind that our reactor inlet we always put it at axial position 0. So, let us put that as 0 and let us say my catalyst bed is of the length L. So, now in this shell let us say that my temperature is T1 of Z, because my temperature is changing along with this axial position. At the inlet it is T1F, but through the shell it is T1 of Z. What happens to my concentration? I am not changing my concentration. So, concentration remains same as C1F, because there is no reaction there is no catalyst in that region. So, at this particular point we have some temperature, let us say T1 0 and concentration C1F, which enters into my reactor. Okay. So, now this T1 0 and C1F enters my reactor, and what happens here? Let us say that my concentration now will change. So, let us say that concentration in the reactor is C1 and temperature is T2, both are functions of Z. So, my products will come out over here, and let us say my temperature that comes out is T2L and concentration is some C1L. So, we have now actually coupled the heat transfer and reaction. So, what is happening? The energy that is generated will get transferred to the shell or the cold reactant that is flowing through the shell. So, we would like to now set up mass and energy balances for these reactors. So, this is my reactor R. So, let us see what happens for my reactor. What is happening in the reactor? The reaction is taking place, and for sake of simplicity let us say that our reaction is A1 going to A2, exothermic reaction. Okay. So, if my velocity is let us say u over here in this of this fluid, then I will consider a simple plug flow reactor, no mass transfer resistances for sake of this illustration. So, my concentration will change according to my rate of reaction. And what happens to the energy balance? My energy balance will take form of this is what we had seen earlier. This is my energy content which is changing along the axial direction. This is my heat of reaction, and therefore, because of reaction there is some energy that is liberated, and this is the energy that is getting transferred from the reactor to the gases that are flowing in the shell. Okay. Now, let us write a similar balance for my heat exchanger. what is happening in my heat exchanger? There is no reaction. So, concentration remains same as C1F, only energy is getting transferred from the reactor side to the gases that are flowing into the shell side. Again the energy content minus, we are assuming the velocity remains the same. So, the size of this tube and let us say the shell is, the diameter is same. So, u remains the same and we have a energy transfer from the reactor to the shell side. Notice here the negative sign has come, because if we take the velocity u in this direction as positive, the velocity has to be minus u in the reverse direction, because the flow direction itself is different. So, now let us try to write the these are two energy balances and the mass balance. So, we need boundary conditions for this. So, what all do we know? For example, we know that the concentration at the inlet of the reactor is C1F, that is my feed condition. So, I can safely write at my inlet of the reactor, concentration is C1F. Okay. What about temperature? T10. I do not know what that temperature is, because all I know is what are my feed conditions. So, I know what is the temperature at Z equal to L or at this location, but I do not know what would that temperature be at Z equal to 0. But I do know that the temperature of the gaseous stream coming out at Z equal to 0 here is the same as temperature of the gaseous stream that is entering the reactor over here. So, I can write a coupled equation, namely the temperature of the gaseous stream that is coming out of the shell is same as the temperature of the stream that is entering the reactor, and which is some value T10. I do not know what that value is, but I do know that T1 at Z equal to 0 must be T2 at Z equal to 0. So, this is my boundary condition at Z equal to 0, and what is happening at the Z equal to L? We need 3 boundary conditions. We have 1, 2 and we have another boundary condition, namely the inlet temperature is known to me. So, my temperature of the gaseous stream in the shell side at Z equal to L is T1F. That much I know. So, now if we look at these 3 balances and corresponding boundary conditions, we see that we have a coupled boundary condition problem. Why coupled boundary condition? Because typically if you have a differential equation and if you know all the conditions, that is all the boundary conditions at one point, then that is namely let us say entry of the reactor, which is what typically happens when you have a single pass reactor or a normal tubular reactor. But in this particular case, we have a tubular reactor, all right, but we need 3 boundary conditions, but we do not know them at any of the inlet or exit point, but we know them some at the inlet point and some at the exit point. That is, this we know at the inlet point, This we know at the exit point, and therefore, we call such problems as coupled or 2-point boundary value problems. So, we have set of differential equations, we want to solve them, but we do not know what this solution is. So, how do we solve such problems numerically? Numerically, we can solve these problems in the following manner, and it has to be done in an iterative manner. That is one way of doing it. Other is to solve a 2-point boundary value problem, but that is too mathematical. So, let us try to look at iteratively how we can solve this problem. If you look at what is happening over here, let us say that I assume some value of T10 and that is my starting point. So, I will say that first step is assume T10. If I assume T10, then I know everything that needs to be solved, because I know 3 conditions. This concentration is C1F, T10 is T10 because I have assumed some value, and T20 is T20. So, I can integrate these equations in a single direction. So, that now this becomes an normal boundary condition problem, no 2-point boundary condition problem if I assume T10. So, then I integrate mass and energy balance from z equal to 0 to z equal to L. So, I will then know C1 at z equal to L, T1 at z equal to L and T2 at z equal to L. That is, if I assume value of T10 over here, then I can simply solve these 3 energy balance, mass and energy balances in a forward direction from z equal to 0 to z equal to L and get these values. Now, of these 3 conditions, I know what should be my T1 at z equal to L, because let us call this as T1L, and according to what I know, that value should be T1F, right. That is, temperature of this reacting stream at Z1 equal to L is fixed, that is my feed condition. So, T1F. So, by integrating these equations, if I know my T10, it should match with T1F. Okay. Now, how do I know that it will definitely match? That will depend upon how good is your guess of T10, or in other words, after integrating I will check this, namely I will say this particular value, is this equal to T1F? If answer to this question is yes, I have solved my problem, but if answer is no, that means my initial guess of T10 was not correct. So, I will go back, make another assumption on T10 and go on repeating this process till I get T1 at z equal to L, T1 at z equal to L matches with T1F, and that is how I will numerically solve this problem. Now, before we look at how we solve this problem numerically and look at the numerical solution, let's try to look at how do we, what kind of qualitative information can we get, and to do that what I am going to do is and let us see whether this works. Okay. No, it did not work. Okay. So, let me redraw all over again. Okay. So, what we said was this was my reactor, this was my shell, T1 at Z equal to L is T1 F, this is my Z equal to L, this is my Z equal to 0, this is my temperature T1 here, T2 here and concentration C1 here. So, this was flowing like this. So, here the temperature is T1 0 and T2 at 0 is also T1 0. By doing this, I will get, by my iterative procedure whatever I said, will get T2 at Z equal to L, T1 at Z equal to L, and let us call this as T1 L. This is what we ultimately want. So, let us this has to match with T1 F is what we want to check by doing an iterative scheme in which we will assume T1 0, integrate these equations in a forward direction from Z equal to 0 to Z equal to L, get T1 L and try to see whether that matches with T1 0. So, now let us qualitatively try to see what behavior will I get if I try to solve these equations. So, on x axis let us put T1 0 and on y axis let us put T1 0 minus T1 L, okay, T1 0 minus T1 L, and let us try to look at qualitatively what these solutions will be like. Now, let's again this is all qualitative argument. Okay. Let us assume that my T1 0 is very low. Okay. My T1 0 is very low, and we saw that if the temperatures are low, the reaction rates are also very low, right. I mean, if you do not recall, we will go back to temperature versus rate, and these are my rate contours, colors low rate to very high rate. So, if my temperatures are low, let us say something like this, then I see my reaction rate is also very low. Okay. So, I would then expect that my reaction will be very slow in the reactor, my reaction will be very slow in the reactor, and therefore, at low values of T1 0, very little reaction in the reactor. So, my T1 L, very little reaction means what? Very little heat generation. So, very little heat transferred to the shell. So, my T1 at this point will be pretty much close to T1 at Z equal to L, because there is very little reaction, there is no heat generation. So, no heat exchange or heat transfer which will preheat the reactant. So, at a low value of T1 0, my T1 L will be pretty much close to T1 0, because very little reaction. So, no change in temperatures across this entire length. Okay. So, that is one limit. Let us look at the other possible limit, and if we say if my temperature is is very high, so high that for the given composition of the feed, that temperature happens to be my equilibrium corresponding point on this violet curve. So, let us say that given this composition of the inlet, my temperature is this particular value, this value over here, T10. Okay. So, what will happen if my entry temperature conditions are such that the reaction is at equilibrium, because I am putting this point on contour of rate equal to 0. So, if at the entry point I have already achieved my equilibrium, then what will happen in my reactor? In my reactor, no reaction can take place, because if the conditions here are such that at the entry point are such that we are at equilibrium, then the reaction can't even start. So, there again won't be any reaction through the entire reactor. So, again no heat transfer to the shell side, again the inlet temperature T10 here will be pretty much close to T1L. That is, we will have some point like this at very high T10. Let me repeat this argument once again. We are saying that we are assuming some value of T10, integrating these equations and getting a value of T1 at z equal to L, that is T1L, and plotting T10 against T10 minus T1L. Now, what kind of solutions can we expect? We will have to actually numerically integrate it, but some qualitative feel we can get by considering the extreme cases. Namely, if temperature T10 is low, then the extent of reaction will be very low, because the rate constants are low. Hence, there will not be hardly any difference in condition from the z equal to 0 to z equal to L, or in other words hardly any reaction in the reactor, therefore, hardly energy transfer from the reactor to the reactant, and therefore, hardly any increase in temperature from T1L to T10. So, we will have a point somewhere like this, where T10 is pretty much close to T1L. Let us consider other extreme where T10 value is so high and is of a specific value such that this T10 corresponds to the temperature which is at which equilibrium is achieved vis-a-vis the inlet composition. So, corresponding to C1F, if T10 value is such that the equilibrium is already achieved at the inlet point. So, if equilibrium is already achieved at the inlet point, no reaction can take place from inlet to exit. So, no heat transfer. So, once again T10 will be same as T1L. And so, as we change my T10 now, the solution, it turns out, looks something like this. Okay. So, both at low and high assumed value of T10, the y axis T10 is same as T1L, and then it goes through a maxima. Now, on the same plot, let me plot T10 minus T1F, and let me use a different color to do that. So, now I am trying to look at, okay, I have already plotted, for example, over here this particular plot is T10 minus T1L versus T10. I am now going to plot T10 minus T1F versus T10. Now, what will be the value of this function? This function will have value 0 when T1 0 is equal to T1 f. So, let us say that this is that point T1 f, that is my feed condition. And what is this line? This is just a straight line starting with T1 f. I am going to cheat little bit to just to make a point. Okay. So, blue line is my T1 0 minus T1 L, my red line is my straight line T1 0 minus T1 f versus T1 0. And what does these intersection points indicate? Let us indicate them by a different color. What does this intersection point indicate? What must be happening at these intersection points? At this intersection point, value of both the functions is identical. So, what does it mean? It means the intersection point T1 0 minus T1 L is equal to T1 0 minus T1 f, because this is my red line, this is my red curve, this is my blue curve, and intersection points denote T1 0 minus T1 L is T1 0 minus T1 f, or in other words these three intersection points denote T1 L equal to T1 f, which is what the solution that we have been looking for. Now, what happened? What happened is that what this is saying is that for a given value of T1 L, I actually have three different values of the temperature at the top T1 0, corresponding to which reactions will take place, or in other words we will have once again multiplicity of steady state, multiplicity of steady state. Again a behavior which is similar to what we had seen earlier. Let's look at the actual plots for ammonia synthesis, and then things will become clear. Okay. So, what we are seeing is on the x axis is the same thing actually, is the value of T1 0 that we have assumed, and on the y axis that is over here we have T1 0 minus T1 L, and this particular line over here is representing T1 0 minus T1 L, whereas the straight lines of differing color are my T1 0 minus T1 feed, okay, with different x intercepts. And the intersection point, I will just show typical ones. These are the three possible values of the top temperatures that we can have for this particular value of T1 f. For example, if I choose this particular value which is shown with a blue line. So, I see that this intersects at three different locations, and corresponding to this T1 f, I have this T1 0 1, another T1 0 2, this particular temperature, right, and third possible temperature this particular value T103. Okay. Now, what happens if I have my inlet temperature or the feed temperature as shown by this particular line, then I see they intersect only at one point. Even at this particular point, these two curves intersect only at one particular point, whereas for all the values of T1f between these two limits, and what is this line I have drawn? This line is tangent to this curve at upper point and at lower points. So, all the T1f values between this range, we have possibility of 3 steady states, and this is what is shown here on the second figure. That is, what we are seeing here is T1 feed versus top temperature T10. So, for a low value of T10, T1f, for a low value of T1f, we have this value of T1f. For any T1f in this particular range, we have 3 steady states. That is 3 different possibilities of top temperature, and for any T1f greater than this value, that is on this side, we are once again have single temperature. So, if you join all this, you will get a plot which looks something like this. So, once again illustrating the fact that for low value of feed temperature, the top temperature will also be low, right, very little reaction. Okay. What is to be noted here is, that is why this delta T was shown over there. Here the delta T is very low, right. But here also, if you look at, for example, if you look at the feed temperature of 500, I am just taking approximate. Okay. So, feed temperature of 500, I can have 3 temperatures, top temperatures, something close to, let us say 520, this point, something close to 520, then 660, let us say, something close to that, and something of a higher value, okay. Let us say 730. Okay. If T1f is somewhere like 450, my top temperature is also 450, this particular point. But what about this point? If T1f is, let us say 800, it is not a very exact straight line. So, let us see, if T1f is 800, my T10 is something like 850, let us say. So, what has happened? Delta T is small here, and in fact, if you go even further, 900, the difference is almost vanishing. So, 900 T1f, T10 is also 900. So, very little reaction on both these sides or even here, but lot of reaction at these two particular points. How do I know there is lot of reaction? You look at delta T. For example, delta T here, the temperature difference between the inlet and exit is almost 160 degrees with this point. This point delta T is even higher, almost 230 degrees, which is the indication that lot of reaction has taken place. So, it turns out that from operating point of view, this is normally considered as a optimal point. But whatever it is, the point is we get 3 different possibilities, and so we could have multiple steady state. Let us wrap up this discussion by looking at how this temperature profiles change. So, what we are seeing here is conversion, or rather this should be temperature versus length of the reactor. So, once again this is my reactor, right, this is my reactor, this is my heat exchanger. So, my reactants are going like this and coming out like this. So, this is my Z equal to 0, this is my Z equal to L. So, what we see is that at the top Z equal to 0, what we are seeing, green is the temperature of the fluid in the heat exchanger and red is the temperature of the fluid in the reactor. So, what is happening to the temperature of the fluid at the start or at the top, both are same, but what is happening to the temperature in the shell, for example. In the shell there is no reaction, so there is continuous exchange of heat. Now, let us just qualitatively look at what is happening in the reactor, then we will go to the exchanger. Now, at the reactor, at this point at the inlet, both these temperatures are same, the heat exchanger side and the reactor side. That means, as little further down in the reaction, the heat exchange rate at the inlet is 0, because there is no driving force, and but there is a reaction there and reaction is generating energy. So, initially the rate of heat generation will exceed the rate of heat transfer and temperature will slightly increase, okay, in the reactor. Now, what is happening in the heat exchanger? The heat exchanger temperature here is the maximum. So, there is a heat transfer. So, this is a lower temperature and this is my feed. So, in the heat exchanger the temperature is continuously decreasing, that is in this particular upward direction from Z equal to L, that is the exit to the entry to the reactor, temperature will continuously increase, or from the entry of the reactor to the exit of the reactor, temperature will be continuously decreasing in the heat exchanger. So, what is happening in the reactor? In the reactor, as I said, initially temperature will increase. Now, it comes little further down, you see that the driving force, that is the temperature difference between the reactor temperature and the shell side temperature, is now increasing and reaction rate is gradually decreasing. So, what will happen? There will be a point where the driving force for heat transfer just matches with the heat generation rate, and beyond this point, because driving force is continuously increasing, the generation is continuously decreasing, the temperature in the reactor starts decreasing. Now, this is what we wanted for our reversible exothermic reaction anyway, that is high temperature in the beginning and progressively decreasing temperature. So, this is how it is achieved by a single operation in which you preheat your reactant using the energy that is generated in the reaction. If you recall our discussion on extent of reaction and temperature, this is how things work here. This is my equilibrium line, R equal to 0. This is the line when this is the line for which delta R delta T is equal to 0, and autothermal operation, it actually, if you plot conversion versus temperature, it actually follows this particular trajectory, which is what we wanted by using adiabatic reactors or by various different ways, and this is now very conveniently obtained in an autothermal reactor itself. But autothermal reactor also leads to the operation in which we have possibility of multiple steady states, where at two different that is starting from the same feed temperature, we may actually have different inlet and outlet different outlet temperatures, and this is a fact that we have to keep in mind while designing the autothermal reactors. So, with this we will conclude our discussion on autothermal reactors, and we will go on looking at a different aspect of reactor design, namely the safety considerations and reactor design. So, we will start looking at that subsequently in the existing. Okay. Design considerations and safety. Okay. Now, the idea in discussing this particular topic is very important, but very straightforward as well. Now, what we saw so far is how different kinds of reactor designs are carried out. We saw few case studies, we looked at the kinetics, we looked at the reactor design, mass balances and so on. Now, even though we try to design our reactors in as safe manner as possible, there are always difficulties associated in controlling some of the reactions, which in a extreme case of complete control failure leads to tragic accidents such as Bhopal gas tragedy. So, while designing the reactors, we obviously do not design for such extreme cases, but one must be aware of the conditions under which we could have disaster on hand. And this is what we are going to look at by with the help of few examples, and why reactors behave in certain manner which make it appear as if there is no control over the process. So, let us look at a few examples, and this is an example which we will first look at the actual examples and then try to understand what is the reason behind such behaviors. Now, first example is multiplicity of steady states in a stirred tank operation. Now, on face of it, nothing can be simpler, or at least it appears that operating a stirred tank reactor at a steady state is probably a very safe way of doing things, but that is not necessarily always the case. So, what we are looking at is an example of sodium thiosulfate oxidation. The reaction is not of that so important, but the phenomena, because this phenomena is observed for variety of different reactors. And the first example what we are seeing is the operation of an adiabatic CSTR, and what we see on the x axis is the residence time. Okay. And what we see on the right on the y axis is the steady state temperature. Okay, steady state temperature on the y axis and residence time on the x axis, and these dots are the this exothermic reversible reaction are the experimental points. So, what we see is that if we start increasing the residence time, let us say residence time is very short. Okay. Residence time is very short, then you expect very little reaction. So, temperature in the reactor is also very low, and it remains low if you keep increasing the residence time. Of course, temperatures are slightly increasing, but they are still on a lower side. But what we see is that if we increase the residence time beyond this, let us say what looks like 18 minutes, the temperature suddenly goes to a very high value. So, there is a sudden increase in temperature. Okay. Let us repeat this process, but now in a reverse direction. That is, we have longer residence time, we have a lot of reaction taking place. So, temperatures are fairly high, and we now go on reducing the residence time, and temperatures progressively decrease. But once again there comes a point where if we reduce our residence time below this particular value, then temperatures suddenly go down. And in fact, if you first of all, so what do we see here? We see a hysteresis, that increasing the temperature, increasing the residence time first gives us this particular branch of solutions, and then suddenly the temperatures go to a very high value. Decreasing the residence time gives us high temperatures, but then suddenly temperatures go down. So, what do we see here? For example, for a residence time of 12 seconds, we see that there is a possibility of two different values of temperature in the reactor. One which is a very low value, and one which is a very high value. In fact, it turns out that if you use proper controllers, we have a possibility of even a third value, and there is another branch which is in the middle, or in other words, three different values of steady states. Now, why is this? How is this connected to the design and safety I talked about? Let us say that you had designed your reactor to operate at this condition using this particular residence time. Now, what is residence time? Residence time is nothing but the volume divided by the volumetric flow rate. So, in the process, let us say that something happens, some fault develops into your pump. So, your flow rate, instead of what was desired, is actually decreases. So, what would it mean? It would mean that your residence time would increase. If the flow rate decreases, residence time increases, and if residence time increase brings it to this particular. So, let us say that you had designed your process for 17 seconds residence time, but suddenly the residence time becomes 20 seconds. What you will have in your reactor is suddenly shoot up, because at this particular residence time the only steady state possible is this particular value. So, what you had considered as a safe operation with temperatures hovering around or 10 degrees, okay, very low temperatures, suddenly you will find a small increase in temperature, you will find that you have reached a very high value of temperature, not a desirable situation. The same thing can be said over here. If you are operating at this point and residence time suddenly comes down, you will have completely shut off your reaction. Now, both turning on the reaction or shutting off could have implications in the entire process, and therefore, one has to be clear as to what is causing this multiplicity and what are the regimes. We will stop here for this session, but look at few examples, more examples before we start analyzing this reactor behavior. Thank you.